Thanks for this intro. First, let me say, when I submitted the proposal for doing this talk here, I did not expect to be put into a room with such a big audience in front of me. Anyway, now I'm here, and first of all, this is not a talk addressed to OpenWRT developers. So the technical level is it's really on a more abstract, almost sometimes philosophical level here. But I thought about it, and I made the decision that this is the most important point I want to get across here to you, and I think I'm preaching to the choir here when I say that we're all interested to keep developing technologies, communication technologies, that allow us to communicate more directly and more authentically. So we need more of the things on the right side and less dependency on the infrastructure that looks like on the left side here. The problem is, for example, in wireless mesh networks, where this is very easy to do, or we will see, it's an interference limit problem that we run into quite fast. So it's not, the performance of the network is not dependent on creating distances that are small enough to get at least some signal to the receiver. It's more or less the interdependencies of multiple transmissions in a shared common medium. And actually, every wireless network eventually becomes an interference-limited network with a growing node density. It's even analogous to society itself, because right now we're starting to live in a society that is attention-limited. The relation attention interference is pretty strong if you look at it. Obviously, the technology that we like to use to build meshes, we refer to it as IEEE 802.11, WLAN, or most people nowadays globally say Wi-Fi, although it's a trademark term from the Wi-Fi Alliance. And the link speeds that these protocol families offer are sort of growing like monotonously. It's really strange to look at the throughput figures that some vendors now give in the range of, I don't know, 7 gigabits per second or something like that, although the hardware itself starts to look really ridiculous. But anyway, this is the most suitable technology that we now have. It's becoming, thanks to Moore's law, extremely cheap, extremely powerful, but it needs one thing to work, which is free channels. And especially 11AC gear is directed toward 5 gigahertz usage. And if you look, for example, in North America, in order to get these gigabit speeds, we must use channel widths in the order of 80 or 160 megahertz even. And then we have the same situation that we know from years ago in the ISM 2.4 gigahertz band. So I'm a fan of wireless mesh networks. In the previous talk, we heard what great things we can do with meshes. And this passion caused me to look into ways how to improve the overall performance of meshes, of true meshes. And there are many spots you can look at improving. This is just one way to categorize. So I looked at rate controlling and power controlling. So these are things that are not really standardized, so there is room for improvement, room for optimization for mesh networks. I also looked at rather sort of fancy things like network coding for some time. And I also had the chance to look at congestion control because I worked for a project that defines the distributed congestion control in the vehicular communication field, so like ITSG5, they like to call this. And when I did all this, over the years, it came to me that there is one strange thing missing here, actually, which is we know that these networks are interference limited mostly, or they all become interference limited in the end. But where exactly can I measure this interference anywhere when I'm participating in such a network? So I'm actually trying to make the point here that in order to make this distributed system robust enough, or at least more robust, we need to implement some way that lets us directly observe what are the resources that are available currently in that channel, in that room. Like right now, in here there are probably there's the 2.4 gigahertz band is buzzing because of probe requests and I don't know, the normal activity with the access points in here. Where in our devices can we see that? And most people think, yes, it's possible, because basically you're just looking at the information that is decodable by the radio front end, and then you can sort of assume that you have a very good correlation with exactly this is the activity that is actually taking place right now. But the thing is, because it's a distributed coordination that is done when accessing the medium, actually it's called distributed coordination function, so pretty straightforward in the standard, which is more or less the equivalent of, so it's mimicking human communications in a sense that if you put several polite people in a room and they want to have a discussion, they do exactly that. So they listen if the medium is free. If it's not free, they back off and wait until the person who is currently speaking has finished the sentence or appears to have finished the sentence. So, and since this is distributed over space, every receiver has a different perception of exactly what is the medium now active or not? Am I allowed to speak or not? And 802.11 works in a way where it just defines sort of a power threshold, or most 90% of the devices work like this. There's a power threshold. For example, yeah, in OFDM, it's only a power threshold. And so there's a power threshold defined, and every node that is waiting to get the next opportunity to transmit is basically waiting until the channel power goes below that threshold. This is a very simplistic shortcut now, but essentially that's the way it works. So for example, this should be a visualization of instantaneous power at the antenna input of a Wi-Fi radio. And this is not a real measurement. This is basically something that I try to come up with a visualization as it actually looks like, but cleaned it up a little bit more. So this is not the real measurement data here, but you see that there are these blocks, and these blocks correspond to individual OFDM frame transmissions around the place, and the green line is the line from which so this could be sort of the carrier sensing threshold at our current receiving device. And what happens is that you see there, maybe it's not so perfectly clear, but there are multiple overlappings all the time. So there is not like a slot structure, because it's a distributed phenomena and everybody has a different perception. It's really like, if we want to have a clear discussion in that room, it would be pretty impossible just via unamplified verbal talking here. So what an actual receiver is trying to understand are those parts that are non-overlapping. And what he forwards to the upper layer is basically just the stuff that he could decode. And that is sort of the fundamental thing that I want to sort of point out, that the whole channel load, the receiver or the upper layers, they don't see the actual utilization of the channel. So there is a sort of loss of information that happens there all the time, because our equipment is currently working like it works. You only get what you could understand, and you get some signal strength information annotated to it. And this is sort of the philosophical part here, that is some media theories. If you, like, keyword is Marshall McLuhan here, they say all the technologies we develop are extensions of our human capabilities. And if you think about it, wireless communication is a little bit, could be said as an extension of our ears and of our mouth. And this behavior here is equivalent to the situation where we are all having sort of electromagnetically, so we have ears in the 2.4 and in the 5 gigahertz spectrum, and when we go into a noisy room, we basically hear nothing. We just hear the stuff that someone is speaking to us, really standing directly and shouting in our ears. That's what we can hear. But we don't hear that there is activity in the room. We don't look for another room, for example, because we cannot even perceive the noise here. And that's a very long message saying that we now made a patch for OpenWRT that when you go for real-time graphs, so OpenWRT has this real-time graph view, before you even connect to anything, before you even see any other, before you do any kind of association or attachment, you see now a third graph additional to the two that were there before. And this third graph just shows you on the current channel that you're listening to, this is the level of activity, like in percent, over time. I thought about doing a demo here, but I think it takes too much time, so I'm just showing you some screenshots here. We call it QBSS load. That I will explain later. But what you actually can do now is we see the actual channel utilization. We see what are the resources left that we can use to communicate with. And this has many useful, applications just because it's observable right now. And we thought, well, isn't it even better if we can tell about the situations, if we can inform? No. The actual reasoning was, now we can observe it at our local node, but it's still difficult to communicate this some way, for example, to clients that want to talk to us. So we looked for ways to distribute this measurement data somehow in order to create a global view of what are the resources in this room currently available. And we thought that we should broadcast these local observations using beacons. And it turns out, if you look into the standard documents, there is already defined a way to do this broadcasting of channel load measurements. And this thing, they call it the QBSS load. And there's already standardized the format how you can annotate this load in every beacon that you send. So you add 7 bytes of additional information to every beacon. Beacon is normal management information that is transmitted by access points in infrastructure mode or ad hoc nodes themselves. So all we did is basically try to implement this in the software stack on OpenWRT. We were aware at that point in time that some access points, for example, the sort of enterprise-grade Cisco gear is already doing that. The reasoning behind this, it enables voice over IP applications to offer a better quality of service because the handover decisions are better. And so we went forward and tried to put this into an open software stack. The patch itself that does sort of the main important things is really, really short. The problem is that I have a background in electrical engineering, So I'm really lousy at kernel hacking, but I have a colleague who sort of has a computer science degree, but he's also completely new to kernel space things. So we pretty much screwed up everything that we can screw up there and made all the memory allocation and all the lockings the wrong way. But we still were adventurous enough. So basically, this is my colleague here, Arthur Linde. He deserves all the credit for the coding. I'm just the guy who sort of suggested it and also managed to get some funding for it by this EU project called Confine. So we were naive enough to do our first trial at the wireless battle mesh in August this year in Maribor. And I will never forget the face of Arthur when we had to sort of quickly find out that our patch totally kernel panics in a situation as is in the battle mesh. So I felt really sorry for suggesting the idea. Anyway, we're currently in the phase of sort of polishing it really to make it sort of to convince subsystem developers to let this in, because it's a rather nasty thing that we are updating fields in a beacon over time. So this is not a usual thing, but we think it's relevant. So we want to go for it. And what it, for example, allows, this rebroadcasting is something like that. So this is a view that you can get when you use a very nice tool called Horst. Highly optimized radio scanning tool is one way. So Bruno wrote it, or is maintaining it, and it's pretty useful when you're doing debugging of mesh links. And now we made a little patch to it, so the part on the right side is new, and the part on the right side just says you, okay, these and these MAC addresses now see from their point of view these and these loads. If you look, they are all operating on the same channel. They are all within communication range. So this is an output you see just with your normal Wi-Fi receiver. So I could demonstrate it right here with a normal Wi-Fi radio. I see access points around here broadcasting the channel, load, fuse, and I see that they're different. So this is a perfect demonstration of it's a distributed phenomenon. Everybody has a different perception of noise. Why is this all so relevant? I mean, it's relevant for the cases that were mentioned in the intro, for example, but there is another thing that there's another reason why I wanted to sort of make this point here, and that is currently there's a lot of activity around the 5. So there are lots of things happening because of technology operating in this. They call it the UNII band, the UNI bands, and this activity. One part of it is due to the cellular industry, looking at it from so they are looking at ways now, very concretely, to use these unlicensed bands. The terms are LTU, or license-assisted access. And I mean, it's a matter of regulation, whether this will actually be put in place. But it's expected that the whole point of doing this is in order to have more control. So cellular industry is looking for ways to expand their domain of control into the unlicensed bands. And the problem is, if this happens, since our Wi-Fi radios cannot understand those differently formatted signals, we will hear basically nothing if this activity in the neighborhood starts to appear. So these are some early measurements that people did that show clearly that the presence of such a, in this case it's an LTU base station, will greatly diminish all the performance that we can out of the 5 gigahertz bands using Wi-Fi. As again, it's a matter of regulation, how strict they will be in this equal access and coexistence. If we really take coexistence and equal access seriously, there is no point in doing LTU or license-assisted access, simply because if you want to have an equal access, you basically have to use the same medium access protocol. Listen before talk, same rights to every node. And then the whole point practically vanishes because the channel code is not such different between those two standards. And I think that it's partly because of this that now this discussion has started, because no, wait, let me skip this. The FCC and the European Commission the FCC is about to, and the European Commission already has put new law into place that now seems to try to make it, how should I say, if you look at the new law, it says that they want to make it impossible that people change the settings on their routers, and they're especially worried about the uni-bands again. And the official reason is always about the weather radars there, but I don't think it's a coincidence that there is now a law being put into place that restricts the behavior of, or restricts the freedoms that we have. And at the same time, there's another secondary user, sort of to say. The primary user is the weather radars here, and the secondary user was always Wi-Fi. And now it appears that another secondary user wants all Wi-Fi users to be as restrictive as possible. That's how I interpret the whole thing. This channel load patch will allow us, if that's the big if we are still allowed to run open software on these things, this channel load patch will at least allow us to detect that there are nearby license-assisted access or LTU base stations that may be the cause of problems there. I think I should come. I have a little comment to make, but I think I skip it. And basically, the message I'm trying to make here is we should treat these spectrum resources as our commons. So, sort of, it's about the right for free speech in an electromagnetic way. These are the same sort of the 4 software freedoms that Stallman talks about. We need them also, and we have to ensure that we still retain the freedom to express electromagnetically, sort of. That's my point here. Questions?
Okay. So we have some more time for questions. If you want to ask a question and you're listening on the stream, please go in the IRC. We have an angel listening there and reading the questions out here loud. If you have a question in the room, please come to one of the 6 microphones. And I see we already have the first one on microphone number 2.
Just a small question regarding the HORST tool, where you made a patch where you see on the right side the QBSS. I didn't fully understand because you said that this QBSS is broadcasted in the beacons, but you could clearly see that normal stations were also shown their point of view of the how much interference they see. How is this done? Because if it's only the access point sending it in the beacons, how can you see the station view?
Oh, it's not the station view. It's basically what I wanted to say is that you see several access points there, and sort of all of those give their individual views.
Okay,
that gives you a global
these
view.
are all access points,
Yes.
all on the same. Okay.
Yeah.
The second question, because you said that some vendors implement this and
Yeah.
it's already in the standards.
Yeah.
If somebody is using the patch, are these interoperable, comparable? So if I have a Aruba workstation, Cisco workstation,
Yeah.
it's okay.
Yeah.
Thanks.
Okay, next question from microphone number 4.
Hello, thank you for the talk. Just a quick question. You had a chart where you showed how the Wi-Fi performance degrades if a base station is nearby.
Yeah.
Do you think anybody will go for it because everybody uses Wi-Fi? That would be a public outcry. I can't imagine that can ever be reality, right? I mean, Wi-Fi would stop working.
We'll see. I mean, I also kept, I'm having the same view. I'm just puzzled.
Thank you.
Okay, I see we have a question up there at microphone number 5.
Hi. I have a short question regarding measurements. Have you looked at how this behaves with throughput from access points? So if you can actually detect before even you can, or before you transmit data, how the throughput will be?
No, but that's an excellent idea. I mean, building an estimator for expectable throughput would be now possible with that. That was, excellent.
Thanks.
Good. Microphone number 4.
Hello, what data do you exactly get from the hardware? And is it similar from all the devices?
Yeah,
or the chips?
The data we get are cycle counters. They are called cycle counters, and for this we're using the busy cycle counters or the receive cycle counters, whatever we like. And these are registers that are being sort of, in most drivers, they're being copied in, so they are available via the Netlink interface. And this patch just reads them out and displays them. It's a very simple thing, actually. And most current hardware or most current drivers are exporting this feature.
So, microphone number 1.
Hi. Do you have an idea how we can keep this spectrum in the commons? So, this is a hard question.
I think the only way we have is to make it visible what we do with it. So this, if you take this further, we can see, okay, my neighborhood is full of stuff, and 90% of it is LTU base stations, so I will certainly try to do something about it, right? But if you cannot see it, you cannot act.
Yeah.
So, now we push in very shortly a question from the internet.
Do these chipsets measure all interfaces or just usage by other Wi-Fi?
Sorry, can you say it again?
Do these chipsets measure all interfaces or just usage of other Wi-Fis?
Do these chips? No, I don't know.
Do you get the question?
If the chips use only the user interfaces?
All interfaces?
All interfaces or just the user interface, especially interfaces?
Or just by Wi-Fi?
Just Wi-Fi, I mean, right?
Okay.
That's what I would say. I don't get it, really.
So just Wi-Fi?
Yeah.
Okay. Microphone number 4.
Yeah, so have you taken a look at Atheros Qualcomm spectrum analysis mode for this actions?
Yes.
And does it actually qualify to supplement your data?
Sure. It's a nice feature. When we played with it, we just had the impression that it only sparsely samples. So it's not... It's
only about every half a second or something.
Yeah,
so.
for estimating channel load, it's not really that usable.
Yeah. But also to get a look at other
you can classify what kind of interferer that is.
Yeah.
That should also be put into visualization mode.
Yeah, because there's no... I know that AVM has options for that on their routers,
Exactly.
but there's no real option on OpenWRT now to do it.
Yeah.
And it's really not that easy to do it by hand, so
Yeah.
would be great to have an option for that.
If someone is interested, please come, let's talk.
Okay, we have time for one last short question. Microphone number 4, please.
I just want, did you have experience with 5 GHz, and is there a possibility to get the information from the client also about the activities in there?
From the which client would you refer to?
The Wi-Fi client, like your mobile phone, or
you mean the Wi-Fi client is typically not sending beacons? Is that what you mean?
Yeah, that's why.
Yeah. I mean that we can annotate it to other management frames, like the probe requests they all send out all the time. It would be a 7 bytes addition, which is really small.
Okay.
That's just.
Okay, for everybody who still has a question, Paul will be in the foyer afterwards, so you can meet him there and ask your leftover questions. Thank you very much. It was a really nice talk. So a last round of applause for him.
Thanks for having me.